Welcome. I recently read an article in the Washington Post that really stuck with me and has relevance to our study of physics. Heather Wilson was a 1982 graduate of the United States Air Force Academy. She became a Rhodes Scholar and later a congresswoman from New Mexico. For many of the last 20 years, she has served on the Rhodes Scholarship Selection Committee, and she has noticed a disturbing trend toward over-specialization in undergraduates. Students who are very high achievers but haven't taken the time or the opportunity to critically consider larger questions that actually drive those specific activities. For example, she says, a young Service Academy cadet who is likely to be serving in a war zone within the year believes there are things worth dying for, but doesn't seem to have thought about whether there are things worth killing for. And of more general relevance to leadership activities, she writes, when asked what are the important things for a leader to be able to do, one young applicant described some technique and personal characteristics to manage a group and get a job done. Nowhere in her answer did she give any hint of understanding that leaders decide what job should be done. Leaders set agendas. As we study physics, it can seem frustrating to have to critically consider a problem and decide on an approach. It can seem more relevant to reach for an equation with the appropriate symbols and our calculator with the other hand. However, it is that critical thinking part, as we set up the problem, as we assess our answer, that are preparing you to meet new challenges both in physics class and in leadership roles that you may have in the future. Welcome, I'm Dr. Courtney. In this problem, we're given the mass of an unknown planet and the escape speed of a satellite from a closed orbit around it, and we're asked to compute the radius of the planet. The idea here is that the total energy, that is, the kinetic plus the potential energy of the satellite, must be greater than or equal to 0 to escape from a closed orbit. So right at the escape speed, the sum of those energies is 0. So we're going to use this to find the radius of the planet and we're given the mass of the planet and the escape speed of the satellite. As we develop this problem, we'll start with a sketch. We have a planet. We're told that the mass of the planet is 2.8 times 10 to the 24th kilograms. So the satellite, which I guess has been in a closed orbit but has achieved an escape speed, then escapes from its closed orbit. We're told that that escape speed is 7.3 times 10 to the 3rd meters per second. So our plan is to set the total energy equal to 0, because then the speed we find is the minimum escape speed that we've been given. Then we need to express each energy. So we're going to express the kinetic energy K in terms of mass, which in this case will be the mass of the satellite, and the escape speed. Then we can express the potential energy. That's coming from universal gravitation. And so we can express it in terms of the gravitational constant, the mass of the planet, that will also include the mass of the satellite, and the radius. And just a quick reminder, that's what we're after, the radius of the planet. So then we can solve symbolically for that radius. Once we've done that, we can substitute the values we've been given. Then we'll consider how many significant figures to use to report our answer. So let's follow this plan and figure out what the radius of the planet is. we want to set the total energy equal to 0. So the kinetic plus the potential energy is equal to 0. That's only true at the escape velocity. So then we want to express kinetic energy 1/2 the mass of the satellite times the escape speed squared plus the gravitational potential energy, which is actually a negative quantity. Negative the gravitational constant, the mass of the planet, times the mass of the satellite over the radius. And we want all of that to equal 0. So this took care of steps 2 and 3. Now we can solve for r. First of all, let's notice that the mass of the satellite cancels, which is convenient because we weren't given that quantity. And I'll leave the algebra to you, but we'll solve for r and get that it is equal to twice the gravitational constant times the mass of the planet divided by, not the radius, we just moved the radius over, divided by the escape speed squared. So then we can substitute values. I'm going to start over here because it's a long number. The gravitational constant can be found in most physics books or other reference materials as 6.67 times 10 to the negative 11. We'll be careful with our units, that is newtons times meters squared over kilograms squared, times the mass of the planet, which was 2.8 times 10 to the 24th kilograms, divided by the escape speed, which was 7.3 times 10 to the 3rd meters per second quantity squared. And with careful calculation then, we find that that radius is 7,205,247 meters. That's a lot of significant digits. Our given values were to 2 significant digits, so we will report our answer that way as well. So the radius of the planet and I'll use scientific notation as well, is about, this will be 7.2 times 10 to the 6th meters to 2 significant digits. How can we assess our answer to see if it makes sense before we leave this problem? First of all, we should start with unit analysis. In our calculations, there are several units to consider. Recall that a newton is a kilogram times meters per second squared, and then we still have times meters squared over kilograms squared. Then we have kilograms from the mass of the planet all over meters squared over seconds squared from the escape speed squared. So if we look here, then kilograms times kilograms divided by kilograms squared cancels. 1 over seconds squares cancels in the numerator and denominator. Meters times meters squared divided by meters squared, those 2 meters squareds cancel, and we are left with a unit of meters, which is what we were hoping for a distance. So the units check out. What about the size of our answer, the magnitude? Does that make sense? One way to make an assessment is to compare it with values for the Earth and the Moon. Mainly because these are readily available in many physics textbooks. So if we check the mass of the planet that we were given, we find that the mass of the planet was less than the mass of Earth, but greater than the mass of the Moon. And with density arguments aside, assuming the densities aren't all that different, we might then think that the radius of the planet should be less than the radius of the Earth, but greater than the radius of the Moon, and that is what we find. So between checking our units and putting our answer in context with answers that are more familiar and can easily be referenced, we have confidence that this is the correct one.